Okay, let's start to prove this Cauchy integral formula. So again, we've explained, at least briefly, that the main part is to prove this formula. And again, our hypothesis is that our cycle has winding number 0 for all z's outside of our domain. And to prove it, we're going to use a lemma that we used when we proved the Cauchy integral formula on a circle, which is that this difference quotient function is continuous on the product of u cross u. So again, it's the difference quotient when z and w are different, and then it's the derivative when z and w are the same. And we proved that this was continuous a long time ago. And this will come into play here. So let's start the proof. And it bears some similarities to stuff we already mentioned about winding numbers. So, and it follows very closely with properties of winding numbers. Okay, so we're going to define h of z to be this integral with respect to w, where z is now treated as the variable here. And this will make sense for z's not on any of the loops inside of the cycle gamma. So this is the set in the plane, which does not refer to the parameterization of the different loops. Okay, and now let's try to explain why h here has to be analytic on this open set. So we'll fix a closed disk inside here, inside of u minus this closed set. And inside here, we can move all of the different loops inside of gamma star to piecewise linear things. So that would be inside of the set of u take away this disk. And then h will be continuous by uniform continuity of the thing we're integrating on this compact disk cross this compact set here. So h will be continuous, and then you need to have continuity to apply Morera's theorem. And so once you have that, then we apply Morera's theorem to the result. And again, you would sort of use a homotopy to piecewise linear things so that you could do an integral over a triangle above and switch them. And so this would be over some homotoped version of our cycle. And so you get here that little h is analytic. And our goal here is actually to show that h is 0, and we'll see that at the end, that h being identically 0 is equivalent to the formula we're looking for. But right now we know that h is analytic. Okay, so how do we show h is 0? Well, we're going to define a new function closely related to h. Consider u1 to be all the points where gamma has winding number 0. And we'll define h1 on this set to be this integral here, but without the f of w minus f of z. It just has f of w here. And for similar reasons, h1 will be analytic, and you'd apply the same tricks as over here. You'd sort of pick out a disk on which you want to show that it's analytic, and then you'd use Morera's theorem to help you. But now the point is, h1 agrees with h on the intersection of these two sets, because h is this difference so both of these would be dw 2 pi I. But so h was given as this difference, but for points z with winding number 0 with respect to gamma, this term goes away because the f of z can come out front, and then you're just computing f of z times the winding number of z with respect to gamma. So if you're at points where this is 0, then I'm just getting h1 here. So they agree on this intersection, and now the point is by assumption, the complement of u is contained in u1. So that was where we just said that for z's not in u, we have these winding numbers equal to 0. So then we get that u1 contains this complement, so then the whole plane can be written as the union of these two things. So now we have capital H here, which I could define as little h on u and h1 on u1. So both of these are open sets, and both of these are analytic functions, and they agree on their intersection, so it's well defined. So this will be analytic everywhere, i.e. entire. And now the last thing to do is to show that it's bounded, hence constant, and it tends to 0 at infinity, so it has to be identically 0, which gives us that h is 0. So h1, as we have over here, this is similar to our argument with winding number. You can send z to infinity in this integral, maybe after homotoping if you're scared about sort of a general cycle here, but you can show that h1 goes to 0 as z goes to infinity, which gives that h is bounded at infinity, hence in the whole plane, because it'll be bounded on compact sets as well. So then by Liouville's theorem, it has to be identically 0. So h is identically 0. And again, for h to be 0, that just means you have this integral equal to f of z times this integral, but this was exactly the winding number times f of z. And this is an incredibly slick proof of one of the most general versions of the Cauchy integral formula.